All right, let's get started. I hope the audio is okay. Yeah, cool. So hi everyone, my name is Rishabh. I'm a senior researcher with Spotify here in London, and this is the guest lecture at the IRDM course at UCL. The title of this presentation is Learning from User Interactions, and I would like to thank M&A for inviting me to this guest lecture today. So we're going to spend about 3 hours talking about how do we learn from user interactions. And before we dive into it, since this is the first time I'm doing any of this online lecturing, and it's like new circumstances in the UK as well, making us do that. So I hope you're really kind of paying attention throughout to the end. And if you have questions, then we do have a Slido link. So you can go and click on this link and enter the event code, which is UCL-talk. And you can post your questions until midnight of 19th March. And then I'll give it a shot at answering some of those questions. And if not, then we can always chat offline as well. Cool. So a brief background about me. So I'm a researcher now with Spotify since 2017. And I finished my PhD in machine learning information retrieval at UCL. And I was doing a PhD under M&A. Before that, and during my PhD, I did a number of internships and visiting research positions at Microsoft Research. And in the meantime, I also we co-founded a startup called UserContext.ai. In general, most of my research interests currently are machine learning for marketplaces, which is the main work I do at Spotify. And in the past, my PhD research has focused on search tasks and user needs, some of which we are going to cover today in today's talk. I also have worked on conversational intelligence, personalizations, and I'm super interested in counterfactuals and causal analysis. So if your interest lies around any of these, then I'd be happy to have any detailed conversation at any given stage. Cool. So looking at today's lecture, the focus of today's lecture is going to be how do we learn from user interactions at scale and in different industrial systems. So essentially what we're going to do is we're going to focus mostly on interactive systems and see how we can learn from the user behaviors and user interactions at scale. So what do we mean by interaction systems? So interactive systems are essentially systems wherein the user has a need and the system helps solve that specific user need and task. So essentially, the user need could be any of like finding information if the user is on a web search portal. If the user is on an e-commerce portal, then the user might want to buy a product. On Netflix and Spotify, you might want to play movies and play songs. In Pinterest, you would go and discover style inspirations, and Airbnb will go and try to find a place to live. So essentially, like you have the user has a need and a task which they want to fulfill, and then they go to the portal. The portal then presents personalized offerings. So essentially, the portal is trying to capture what the user preferences are, what the current needs are, and then maybe learn some user representations of the users and present some personalized solutions. So this is where the user is essentially leveraging the representations to offer personalized results by developing user models and then ranking content based on the user profiles that you have developed. Then essentially what happens is like the user interacts with these personalized offerings. And in the interactions, the system, the machine learning system and the background systems in place would log such user interactions like clicks, mouth gestures, interaction sequences, and a bunch of like temporal activity as well. So basically, once we have logged these interaction signals, then the system designers can use this information to detect satisfaction. So essentially, we want to understand like how do we know whether the system is performing as per expectations. So we have to develop these metrics which evaluate how good or bad the system performs. So this is essentially what the underlying world of learning from interaction entails. And this is the right motivation for this talk, because in this talk, we're trying to introduce the students to essentially this world of interactions and how the different companies across the different spectrum and different domains are leveraging user interactions to develop increasingly sophisticated models. So we're going to divide this talk into 3 parts. In the first phase, we're going to start with understanding user tasks and needs. In the second phase, we're going to learn user representations based on these user interaction signals. And in the third phase, we're going to present insights around how do we look at interaction information to develop metrics and for large-scale experimentation across millions of users at different companies. So let me briefly motivate this work and this talk by giving a few industrial use case examples. And we're gonna in the next 5 to 7 minutes, we're gonna lay the foundations of this lecture, give the background on why this study and this talk is important, and then eventually we're gonna go towards like the specific phases. So in general, if we see that there's a wide variety of interfaces to solve user needs. So if you have a search need, then you can go to Google or Bing or Yandex. If you want to have a conversational type of interaction with the agent, then you can go to Siri, Cortana, Alexa, and a number of Google Home appliances. If you want to buy something, then you go to e-commerce platforms. If you have some media recommendations, then you want to satisfy them using Netflix, Spotify, and so on. And essentially, across these different interfaces, there is a huge difference in the way the users interact with these. So this could be in the way the users express their need. So some systems are query-less systems, whereas in the other systems, you have to type in a query. And the user consumption behavior is also different, because if you go to google.com and then search for something, then you'll have to click and then you read a result. Whereas if you're on Netflix and you maybe are streaming a movie, and then you don't have to you don't need to query something, because there is a homepage at Netflix or Spotify which will give you recommendations without even letting you, or without even waiting for you to ask a specific query. And then, of course, satisfaction signals across these different interfaces differ. So let's just take a brief, quick look at some of these in a bit more detail and understand how truly they are different. So if you're looking at a web search systems, then we're going to look at three different questions, like how do users express their need, how do they interact, and how do we know whether the user is satisfied? So we're going to start by looking at web search and then walk through some other different industrial use cases and show that there is a lot of heterogeneity in the way the users interact and in the way in which systems can understand whether or not the user is satisfied. So if you're looking at web search, then the user essentially types in a search query, and then they interact by clicking the results. Maybe they use their mouse on, if they're on their laptop or desktop, to hover around and then click on a result. They go to the result page and then maybe read it for a few seconds. If they don't like it, they might come back. If they like it, they might read it for a longer time. And this is how we get to know that the user was happy with some of the results which we showed or not. So if the user is clicking on a result and then coming back within 5 seconds, then we know that the user didn't really like what they were reading. So that means that result was not a satisfactory result. On the other hand, if the user clicks on a result page and then goes and spends 2-3 minutes reading it, then there is a good likelihood that the user was actually happy with that result. So this is how this kind of thinking can let us think about how do user interactions behave in a web search domain. Looking at conversational intelligence, it's completely different. I mean, if I'm talking with my Google Home device or Alexa, I'm not typing a query. I'm literally having a voice conversation. So I'm going to ask a question and then expect the system to understand my question and understand my need, and then provide me responses. So this is where the modality of the input changes. So instead of typing in my text query, I'm going to pose a vocal question. And if you look at the differences in how the users behave differently across these two platforms, so in search, when I'm on google.com, then I type in few words query, whereas when I'm talking with Alexa or Siri, I'm posing my question as a proper question. So the amount of information users provide is also different. And then the interactions, I cannot really click on anything because it's a voice medium conversation. So then I'll have to maybe ask my Google to pause. No, this is not what I'm looking for, and then ask a follow-up question. So again, the point being that the way the users interact is completely different in a conversational intelligence system. If you're looking at e-commerce, then some of these Amazon, Flipkart, Taobao, these are some very, very different portals, because here you want to buy a product and then you type in a product specific search query and then you interact with the results. Maybe you save an item for later, maybe you just buy it right away. And this is these are the interactions which Amazon can try to understand whether you were happy with the results which they showed or not. If you're looking at media recommendations like Spotify or Netflix, then if I go to the Netflix homepage, then I don't even need to type a query. The Netflix homepage shows some recommendations to me, and maybe I'm just okay with one of those recommendations, and then I just click and start streaming. So again, this is mostly a recommendation and query-less scenario, and we don't expect the users to query And like Netflix does provide a proper homepage wherein like people can start consuming content without even like explicitly asking for something. So again, this is drastically different than how a search system or a conversation system would behave. And this is not just about like consuming media, it's also about like consuming food and all these like other e-commerce companies and marketplaces which are coming out. So Deliveroo and Uber Eats are these platforms which make the user buy food, and then like there's a delivery person which delivers the food to you. So this is where like you're expressing your food needs in the type of cuisines you want. So you're essentially going to go and maybe query for a restaurant or query for some food cuisines, and then the system is going to show you some results, and then you're going to click on them. And if you like it, then maybe you're going to place an order. If not, then maybe you're just going to abandon the session. So again, very much difference in how you interact with a normal search engine versus like Uber Eats versus a media platform like Spotify or Netflix. So essentially, there's a lot of recent work in the industry in order to understand user behaviors and user interactions, because as you've seen that a lot of these companies essentially rely on better understanding users and then predicting whether the user was satisfied with the content they served or not. So that's why a lot of research across different companies has gone into developing these methods which learn from user interactions essentially. And this is why this talk is and this lecture is important. So we're going to cover a lot of papers, and I'm going to give you a whirlwind overview of the last decade or so of the published literature from across like industry and academia on some of these topics, which are of like very, very important, very much important to a lot of these like industrial companies which work with user-centric systems. Cool. So again, as I mentioned that we're going to start by looking at these three phases, I'm going to next spend a couple of minutes trying to lay the groundwork of what is it that we're going to talk about in each of these phases. And then we're going to start looking at the first phase. So in phase one, we are talking about understanding user needs and tasks. And this is where we pose the question that what is a task and why are tasks important? And then we begin by looking at different tasks across different devices and different interfaces. And then we essentially dive deeper into understanding tasks in the web search space. That how do we understand the intent behind a query? How do we understand what the session is about? How can we develop models which really extract the task the user is trying to do? And then we present some insights on how do we evaluate some of these algorithms. Now, this is web search. But what happens in recommendation systems is something different, because a recommendation system does not necessarily rely on the user issuing a query. So there we have to understand user intents in goal, and how do we define user intents, and how do we predict user intents. So they allow us to understand why is the user here? What is it that the user wants the current session? And how can the system best serve those content to the users? So all this is something which we're going to discuss in the first phase, which is understanding user tasks and needs. In the second phase, you're going to learn about how do we leverage this interaction information to learn user representations. So essentially what a system is going to do is it's going to look at your preferences. So given a user's historic interactions, they're going to develop these preference models and user interest models, and then try to personalize the offerings based on the learned representations. So we're going to look at a number of different approaches in which these representations could be learned. So you may have covered some of these in some of your courses or electives already. So we're going to spend some little time in talking about some of these brief established ones. And then towards the end of this phase, I'm going to mention some really recent state-of-the-art representation learning approaches. So essentially, the goal here is how can I learn a representation about the user, which helps me provide the user with a personalized offering. And in the end, what we're going to look at is how do we leverage all that we have done so far. So we know that this is what the user's task and need was. This is how they interacted. And then the goal is to predict whether or not the user is happy. And why do we want to predict whether the user is happy or not? This is because as a system designer, we want to design systems which are increasingly better. So in order to measure system performance, we need to have proper metrics and experimentation systems in place. So this is where we're going to start by looking at ways in which we can elicit feedback from the user. So we're going to talk about explicit feedback, implicit feedback, and also satisfaction prediction models. So in the first part of the video, so this lecture is divided into two parts. And in the first part of the video, we're going to mostly focus on the first phase and maybe briefly start with the second phase. And in the second part of the video, we're going to talk about leveraging interactions for metrics and experimentation. And again, as I've said before, there's a Slido link at the start of the presentation, which should be accessible in your slides. So if you have any questions, feel free to post those questions there. Cool. So in the first phase, we're going to start by looking at understanding user tasks and needs. So what are tasks and why are they important? So if you take a step back and look at where we are in 2020 in the online digital space, we have a lot of different companies catering in a lot of different domains like music, videos, health, shopping, cooking, finance, and so on and so forth. So essentially, search and recommendation systems are everywhere. But understanding users is really hard. It's not that easy that a system really understands what we really want and then serves us the perfect content. So we have to spend and interact with the system for like few minutes for the system to understand what is it that we really want and then show that content to us. So if you're looking at search engines, then oftentimes when users go to a search engine, they have a task in their head. So some of these tasks are simple tasks like what's the time in New York or what's the value of one Bitcoin in US dollars. Or oftentimes there is a very complex task like planning a trip or planning a wedding. So a task which is complex, the user will spend a number of search interactions and a number of sessions across a number of days in order to accomplish these complex tasks. So essentially, what we want to convey here is that task motivates user interactions. So users come to the search engine to accomplish tasks. They don't just wake up and say, hey, I want to type some query. So maybe let's just go to google.com. They have a need. They have an information need, which they quantify using their words, which they type in using the search bar as the search query. So essentially, the interactions which users have with search systems are motivated by the task they have. So what is a task? So a search task is an atomic information need resulting in one or more queries. So there's a very seminal paper from Rosie Jones back in 2008 at SICM, which defines what an atomic information need and a search task is. So a search task essentially could be very simple, like I want to find the time in New York right now, or I want to find what's the London weather going to be tomorrow. So essentially, these are simple tasks. But oftentimes, we have a set of related information needs, which make a complex task. Like if you're buying a house, then that's like a multi-week process. You're going to spend a lot of time inquiring about a lot of different aspects about buying houses. Same for planning trips, same for planning a wedding. So a lot of these tasks are essentially very complex tasks, which gets divided into subtasks. And for each of these subtasks, you might query the system and then interact with the results. So why is the understanding of task important? So if the system is able to understand what task the user is trying to do, then we can do long-term predictions. So essentially, like if you start a task of like buying a house, then we know that the user is engaging in this task. So then we can do in-task personalization because we know this is the task the user started and the user is going to continue doing this task for the next week or the next few days. So we know this is the information need, and then we can better show the correct content to the users. It also helps in doing cross-user collaborative ranking. So essentially, some of these tasks maybe a new user is very new to that domain and they don't know what are the different aspects of that task. Versus some other users might be expert users in that domain and they really know what this topic is about, so they know what are the right queries to formulate. And a new user may not even know what is the right query term or the query text, which will give me the right results. So this is where if we have this task understanding, then we can use insights from these expert users and then derive these search ranking algorithms, which help really like novel and novice users do a better job with their current search questions. Again, if we know what the task is, then we can as well just do some predictions and maybe show some relevant advertisements. So if you're planning a wedding, then we know that we're going to look for some of these like local logistics companies, so we can start popping up some of those advertisements and provide more contextual results to the user if we know that this is what their task is. So all in all, task understanding is really beneficial for the user as well as for the system. So let's just start by looking at some of these examples of tasks across different interfaces. So we're going to start with some of this about 2 decades old taxonomy, which is given by Andre Broder. So essentially, they have divided these search queries into different types like informational, transactional, and navigational. And then there is a follow-up work from coming in from Google folks in 2009, wherein they've further divided these different query types into finding simple and finding complex things, maybe exploration and learning about things, navigating, and something else. And essentially, if we go a bit more further, then there is very nice work coming in from Microsoft Bing, Bailey et al. In 2012, wherein they're looking at subdividing some of these tasks into very specific, concrete tasks, like finding a specific fact, or finding a job, or finding real estate, or you might be browsing a social network, or you might discover some leisure activities, or you might buy a product. So again, like as we look through some of these are like really specific tasks, which some of these people have been able to tease apart, and like create a taxonomy around. So once we know what type of tasks people perform, then we can say how popular some of these tasks are. So essentially, if you look at typical web tasks, which people perform across different sessions, then one of the top ones over here is like monitor frequently updated information. So maybe there's some event going on, like the current coronavirus scenario. So like new updates and new news comes in, and then like the user goes onto the search result page and then retypes the query, and just to kind of keep updated with the latest information. Also, people use these online platforms to browse social network. So again, browsing a network, finding information, and watching online videos for entertainment. These are all popular tasks which people do across the web. And we can also look at some of these search tasks, because in the previous slide, we were looking at some of these web tasks which you do on your browser or on your phone. But then on search, you can maybe query for some information, like discover more information about a topic, or maybe compare a different product or different services. If you're looking at, let's say, a comparison task, like I want to compare 2 products, then this is a very complex task, because we can break it down into subtasks. Like I want to explore the dimensions of comparison. I want to compare and compile a list of choices. Like I might come up with like 5, and then I want to have a fair comparison across those 5 choices. I want to find details about a specific choice, read reviews, and read side-by-side comparisons, or act on some of these comparison decisions and go and buy a product. So a comparison task is really a very holistic task, which might end up in a purchase decision as well. So again, like the baseline point over here being that if you have a complex task, then there are these subtasks which we can divide a complex task into, and then act on each of these independently. So we looked at some of these examples in desktop search. So what about digital assistants? So again, like we know that they are very different from traditional web search. And essentially, we have a lot more verbal interactions, and there's like a plethora of new tasks like reminders and everything which come up here. So if you look at some recent work in 2017 from our group, then we looked at Cortana, and we looked at Cortana is Microsoft's desktop conversational agent. And if you look at some of the tasks people do and the use case scenarios of Cortana, then people are using it for general search, but also finding their stuff, like finding local files and folders. But also people do really want to find instant answers. So, I mean, I might have a question that when is the next Wimbledon match scheduled? So, I mean, that's a question I can post to my conversational agent and get answers for. And there's a lot of people using these agents to set alarms and like provide different commands. So again, this is very, very different from the kind of tasks people do on a traditional search interface. If you're looking at some top commands, people like set reminders, set alarms, music controls, and they make calls. They ask the platform to open up the camera on their phone and so on. If you're looking at answers, then people really ask weather questions a lot. And a lot of times people use it for math, for news answers, for time zone queries, and so on and so forth. So again, these are the kind of questions people start asking the moment they go and interact with the conversation agent. If you're looking at voice-only assistants, then there's no textual input at all. And it's a lot more conversational in nature. So of course, like the kind of tasks people do is going to be drastically different. So some of these tasks people do on voice assistants could be, again, like streaming music. I stream Spotify using when I'm at home using my Google Home device. So again, like it's a very common and feel it's a very common use case for using voice assistants. So again, the underlying point over here being that a lot of these tasks are very different across different platforms, which is expected because different platforms serve different information needs. So the question is, given that we know that users try to perform different tasks, and understanding tasks is going to be really helpful, how do we find which task the user wants to accomplish? So essentially, the solution over here would be that we want to understand their queries. Because in a search portal, the user is specifying their query based on the information need they have. And if the system is able to understand these queries, then it can provide relevant suggestions and results. So we're going to look at, like in the last 2 decades, what all have people developed. And some of these models have, some of these preliminary models in the 1990s and early 2000s have been around query intent understanding. And then people moved from looking at specific query intents to sessions. And then we started looking at like, hey, look, a session is not important. Maybe understanding task is a lot more important. So we got in the next 5 to 10 minutes, we're going to start by looking at understanding some of these query intents and then shift towards understanding user sessions in a search portal, and then go on and proceed towards understanding search tasks. Cool. So this brings us to this part of this talk on understanding user task in search. And we're going to start by looking at understanding query intents and how do we extract intents from the query text. So we know that search queries are often very ambiguous and they're underspecified. They might have different interpretations, and understanding and identifying the intent behind the query could help us in distinguishing the different facets of queries. So intent understanding is really very helpful. So primarily in the IR community, people have relied on 2 major approaches for intent understanding. So the first one is query classification, that maybe we have some predefined intents in which we can group queries. And then the goal would be to classify a new query into one of these pre-existing intents. Or if we don't have these predefined intents, then maybe we can do clustering. So query clustering will allow us to kind of work in cases wherein we don't have any predefined intent groups. So if you're looking at classification, then what type of predefined groups there could be? So one of the groups is like query groups, which we looked at, like navigational, information, and transactional queries. So essentially, back in 2002, Andrew Broder did some work around classifying queries into 3 different types of queries. So the first one is navigational, which is really like you're looking for a specific thing, that I want to go to facebook.com. So my query would just be Facebook. So we know that I want to navigate to a website, and I just issue a navigational query. On the other hand, you can have an informational query wherein you're trying to collect a lot more information. Or a third type of query could be transactional query, wherein the intent is to perform some web-mediated activity, like get some quotes of the insurance, buy some online stocks, or subscribe to New York Times, and so on. And if you look at like online searches, then at least in the 2010s and early 2000s, a lot of these queries were essentially informational queries. Now, how do we classify these queries? So essentially, like given query text and given user interactions, can we classify some of these queries into any of these 3 buckets? So yes, we can. I mean, we can start by looking at some of these query features. So I can look at the query term. So if the query term has a company name like Facebook or an organization name, then I know that this is most likely to be a navigation query. We can start by looking at click entropy as well. So click entropy essentially says like how many like how different are the results which the users are clicking on. So most of the users who issue a query like Facebook, they would essentially go to facebook.com. So that means the click entropy for a Facebook style query is very low. Versus if you're looking at like fancy dresses, then different people across different regions and across different points of time are going to click on multiple different results. So then for that query, the click entropy is going to be high. So essentially, if maybe the click entropy is super low, then there's a good chance that the query is a navigational query. Again, we can also look at like some domain information, some query length, and post-click behavior to kind of compute some of these features and then train a model to predict whether the query is one of these tree groups or not. Cool. So we looked at like one query categorization, which is navigational, informational, and transactional. But oftentimes we want to do topical categorization of queries as well. And this is where like we can start with some existing topics. So we can say that, hey, look, I have a predefined set of topics in which I want to categorize some of these queries. So ODP, which is the Open Directory project, is it's an absolutely amazing topic ontology, which is available to public to kind of consume and build models upon. So essentially, like it's a cross-source effort. It has 15 top-level categories, and it's kind of human curated, and there are tags. So the official project is closed, but then like you can find a static publicly available copy at this DMOS website. So essentially, what it gives us is like there are these topics and subtopics, and there is like website tags which each of these topics. So you can train your classification models on some of these website content information, and the corresponding topic and subtopic are the labels which you can train your classification models on. And essentially, like a lot of these internet companies which are doing a lot of search personalization rely very heavily on some of these topical categories. So if I want to create a user profile, then I can look at the past 1 month of your search history and then go for each of these queries, go and find the corresponding topic. And then I can learn the different topical distribution based on your interest. So for a user based on the query in the last 1 month, if we do this query classification with the topic, with some of these ODP topics, then we can get like a user vector, user representation in the topic space. Now, once I have that representation, I can do all sorts of re-ranking and personalization based on how I want to serve content to the user. So again, like this is something which we can do with manual pre-existing topics, but oftentimes we don't have these topics available. And then we can rely on some of these like LDA approaches. So LDA is essentially latent directional allocation. It's coming in from a seminal work way back in 2003, David Blee et al. At JMLR. And this is essentially like a latent variable model, which gives the different topics in a collection of documents. So it's a generative probabilistic model wherein the emphasis is on a hierarchical model, which says that I'm going to pose that my documents are a mixture over topics, and my topics are a mixture over distribution over words. So then each document can have multiple topics, and each word can belong to multiple topics. And this is a totally unsupervised model which can extract some of these topics for you. So if you don't have topics, then we can throw a lot of data through LDA and then extract these topics, and then we can train some of our classifiers. So understanding the topics, understanding these classification techniques allow us one way to understand what the intent of the query is. But if we don't want to do classification, then query clustering is another approach in which we can find out the intent behind a specific query. So there are a number of approaches, including sequential clustering, session-based clustering, k-nearest neighbors. And we're going to talk a bit about some of this random walk-based techniques, wherein we're trying to look at a click graph and then do random walks and then do query clusters. So let's just spend some time looking at this figure here. So if you go to a search engine, then if you type in a search query, you might click on n number of results, right? And essentially what this work from Nick Raswell and Sikaya 2007 proposes to do is that we can look at a bipartite graph between the query and the results. And then we can do random walks on top of this graph. So if you look at the query panda, then you're going to click on some of these images. But then you might also click on some of these images if you query the term panda bears. So again, like there is this relation between a lot of these results, and you're going to click on a result maybe from n number of different queries, because there's a lot of overlap in the results we show across different related queries. So what this says and what this means is that now if we know that for this query, these are the set of results the user clicked on, then we can create a bipartite graph with different types of nodes. So the two type of nodes would be the queries and documents, and an edge between the two nodes would mean that the user clicked on this document for this query. And we can now create this graph between these nodes, between the query and documents. And then the edge could be based on how many users actually clicked on this result for this query. So now that gives us a bipartite graph and like a graph to work with. What we can do is we can start doing random walks on this graph. So I can start with a node and then associate the click count for each outgoing node from this current node. So this allows me to define a transition probability from each node to the other. So now if we randomly pick up any node on this graph, then we'll know that among all the outgoing links, how many times did the user click on one particular node? And that would give us the transition probability of going in from this specific node to the other one. So essentially, this allows us to quantify what's the probability of going from a particular node I to a particular node J. So once we have these probabilities, then we can start doing these random walks. So once we do a random walk on graph, so random walk is essentially starting with a node and then probabilistically sampling which next node should I go to, and then continuing this process. So if we do a random walk on such a graph, then doing this random walk would generate the weights of the edges, and then we could do a clustering of nodes based on some of these random walks. And once we have the clusters, then we can get to know what the intent of some of these clusters are. So the idea over here is that a cluster which is like closely knit together will have kind of same intent. So if you're looking at like Apple as a query, then Apple for fruit would be a separate cluster, and Apple for some of these Apple products are going to be in a separate cluster. So some of these clusterings can help us in disambiguating some of these queries. So this is how clustering can help us in identifying the exact intent behind a query. Cool. So far, I mean, this is again like a lot of work around this was done about like a decade and a half ago. And we've made a lot of progress in the community and in the industrial systems now. So we moved on from queries to more of sessions and task understanding. So in the next 5 to 10 minutes, we're going to look at what some of these task understanding modules are and how do we develop them. So before going into tasks, what we can do is like we can start looking at sessions. So what is a session? So a session is essentially a chronologically ordered sequence of user interactions. So when a user goes to a search engine portal, then they start by issuing one query, and then they look at the results, they come back, they issue another query, and they can keep on doing that for a certain amount of time. So if you're looking at a continuous time frame and you're looking at the queries within that time frame, then that gives you a session of queries. So once we have the session, then we can use the session information to do a lot of good modeling. So what we can do first is if I have a query log, so a user comes to a platform and then they issue like 15 different queries. So what we can do is we can segment these 15 queries into different sessions. So maybe there's a huge time gap between the 5th and the 6th query. So maybe the user was querying for 3 to 4 queries, and then they had something to do. They went off their laptop. They came back in like out of 5 hours. So then we can look at the time gap between two queries and then start segmenting these query streams into sessions. So again, one of the ways of defining session could just be if the gap between two adjacent queries is more than 30 minutes, then we're going to divide these into different sessions. Now, sessions allow us to look beyond queries because now we are looking at a query group, a continuous query group at a time. And then, I mean, the hope is that the user is going to maintain the context of what they're querying about. So one of the assumptions which people have made recently is that the sessions could be the atomic search task. So maybe like we can have this assumption that if the user is interacting with the search engine in a session and the session has 5 queries, then all these 5 queries belong to the same task. So a session is a proxy to understand what the atomic search task the user is trying to accomplish. Now, if you do session, then session information can help us understand the user needs. because one is we can look at the prior queries in the session, and that would give us a lot more understanding about the query context. So if we know that the previous 3 queries were about this topic, then the next query can be disambiguated based on what context the previous 3 queries were on. We could also do a lot of like search result re-ranking. So we know that for the previous queries, these are the results the user did not like. So then we can use that information and then do like better personalization within session. We can also start by looking at predicting user satisfaction. So if I know that the user really didn't find anything in the session, they abandoned and went away, then we know that the user is unhappy. So we were not able to surface the right result to the user in this session. So it also helps in understanding the performance of these search rankers. So far we have looked at some of the ways of defining sessions and why sessions are useful. But then we asked the question that, is session really a good proxy for task? So again, the point we try to make here is that sessions don't necessarily represent an atomic information need, and users often multitask in a session. So if you look at, again, like if you look at a session and the session is divided based on a time gap between queries, then oftentimes you're looking at booking hotels as well as finding flight tickets, which may be two separate subtasks, and the user might be doing them in the same session. So a session need not be just about one task. And we did some analysis to look at the number of tasks the users performed in a session. And the distribution really is kind of spread out. So one of the findings which we got from that analysis was that more than 70% of sessions are multitask. So the assumption which we had that one session is corresponding to one atomic task, that's not true. Because as we can see, like more than 70% of the sessions are really multitask sessions. And the users differ based on their multitasking habits. So some users are really multitaskers versus some users are really like single taskers. So they are gonna just do one task in a session. And there are certain topics which are prone to multitasking than others. So if you're really maybe you're doing some literature survey, then that's like a hard topic. You're going to spend the entire session querying about that topic. Versus if you're watching a movie or if you're like listening songs and you're going to search for a few songs, maybe listen to them, and then find something uh, other to do in the current session. Also, we looked at that oftentimes such tasks span across multiple sessions. So 75% of the tasks which were considered in one study, they kind of spanned across multiple sessions. So again, you need not complete your task in a single session. You might go away and come back and resume your task. So all this highlights to the point that sessions should not really be the focal units in information retrieval. Even though we have developed over the last 20 years a lot of very good machinery around understanding sessions and doing in-session personalization, but then the point we are trying to make here is that maybe sessions are not atomic, and some of the results we are seeing are showing that indeed sessions are not atomic, and we should look at tasks instead and try to find out these tasks from across these session informations. So this is where we go to the next part, which is how do we go from sessions to tasks? Sorry, there's a typo here. This should be sessions instead. So in the next 10 to 15 minutes, we're going to look at ways of extracting task information from such logs. So we have multiple users coming in and interacting with the search engine. And so we have access to like a millions of different search queries. And the problem we pose is, how can I extract task from the query log information? Okay, so what we're going to do is we're going to start by looking at task extraction techniques. And then we are going to say that, hey, task is really complex. So maybe we can divide a task into subtasks, and then we should perhaps look at understanding and extracting subtasks. So once we do that, then we're going to talk about like extracting hierarchies of tasks and subtasks, because if you have a complex task, you can decompose it into subtasks, and maybe the subtask in itself is complex. And that would mean that we even further subdivide that complex task into further different subtasks. So that means like we will have to look at some tree-based hierarchical approaches of extracting these task and subtask hierarchies. So there has been a lot of work recently in the last few years, in the last like 10 years or so, on understanding and extracting some of these tasks. So we're going to consider a couple of these approaches and walk you through how the research community's thinking has evolved around these problems. So one of the first papers which extracted these tasks was from Lucis's back in 2011. So this was looking at identifying tasks from a search session. So you have a query log, which is QL, which is essentially a continuous stream of queries. And what we can do now is we know that we can use time gap heuristics to divide a stream of queries into different sessions. And once you have a session, then we know that some of these queries could belong to one task, and maybe some other session might belong to some other task. So maybe we can do some sort of like clustering to find out which sessions are about this specific task versus some other sessions. So essentially, if you want to do session identification and task understanding, then one simple idea is to do time splitting based session and task identification. So the idea here is that if two consecutive queries are far away in time, then they're likely to be unrelated. So if a user ends the search query right now and then comes back to the search platform tomorrow, then there's a good chance that the user is going to have a different search task when they come back again next day. Now, a time-based splitting is really easy to implement because then you just linearly scan through your query log, and then the moment you know that there's a huge gap between two adjacent queries, then you say that the task ends here. On the other hand, we can also look at some clustering-based techniques. So the idea over here is that the queries could be grouped using clustering algorithms, which exploit the query similarity and query features. So we can look at a bunch of queries and then compute a number of distances, right? So a distance could either be content-based, like are these two queries sharing the common terms and common characters? So again, we could look at some Jaccard-based distances or normalized Levstein distances to compute distance between two specific queries. Or we could look at semantic distances. So we can say that Wikipedia is going to provide me with the concept space. So we can look at, like, let's say 1,000 documents of Wikipedia, and these are going to represent the 1,000 concepts and topics in the Wikipedia document space. And then we can find distance of each query with each of these 1,000 Wikipedia documents and say this is the representation behind this specific query. So essentially what we're doing is we are representing a query in the Wikipedia document space. So that's the wikification of a query using the vector space model. So now once we know that this query's similarity to these 1,000 random Wikipedia articles was these distances, that 1,000-dimensional vector will give me the representation for this query. Now we can also obtain this representation for any other query, and then that will give us two of these 1,000-dimensional vectors, and then we can do a relative cosine similarity difference and distance calculation for these. So again, these are two ways of looking at some distance computations. There's a lot more work which has happened in quantifying some of these embeddings using deep learning and neural networks. And again, you can use some of those approaches as well to quantify distances and similarities. But once you have the distance, maybe you can combine some of these distances using a convex combination or a condition formula, which will give you a way to quantify how close the two queries are. And once you have the distance function, then you can do any sort of clustering here, right? So we can look at a bunch of sessions. Within sessions, we can have a look at these queries. We know that we can quantify distance across any pair of these queries. And then we can do any of these like clustering approaches. So we could do a k-means clustering or a DB scan style clustering using any density-based approach. We could do a sequential clustering. We could do a graph-based clustering, which would give us the sessions which belong to the same task. So essentially, you start with the query log, you divide it into sessions, and then we are clustering sessions to give us tasks. So this is the approach which these people took to extract tasks. Now, the problem here is that often we end up with noisy clusters, and we have little control over the task clusters which are formed because it heavily relies on how good our distance computation techniques are. So then follow-up work asks this question that can we leverage additional information while clustering? So there's a line of work coming in from from our group about a few years ago, and also some work from Microsoft research on this, which is essentially around entity-based task extraction. So the goal here is that people want to capture this insight that often when we are searching for entities, then people perform similar type of tasks. So if you take an example of London, so London, people ask for like maybe London restaurants, London weather, time in London, and these are the same tasks people do for any other city like New York or Barcelona. So people are gonna find out the weather in Barcelona, find out restaurants in Barcelona, and maybe just kind of say what's the time in Barcelona right now. Same for different entities like Shakira and Beyonce. Like people are gonna search for their albums, and so on and so forth. So the point here is that oftentimes the tasks people do for a specific entity are the same. So maybe there is information in the entities in the search query, which we can use to better understand what task the user might do for that query. So this is where one of the first steps we have to do is like identify the entities in a query. And then once we have the entity identified, then we can do clustering of terms that tend to occur with this type of entity. So essentially what this means is that we can use some of these like off-the-shelf tools to tag entities and find out the category of entities. So we know that London and Barcelona both are cities. So then we can look at all the kind of queries which have the same entity category. Then what we can do is we can look at some of the terms which occurred with these entities and then start clustering them. So once we use some of these terms, which are very common across multiple different entities within the same entity category, then this gives us a way to look at and extract some of these like cluster of terms. And some of these clusters of terms would give us a potential task which the users do with this entity category type. So again, this is another way of extracting what task people might do with an entity like a city or an entity like an artist or any of such different entity types. So one of the other approaches I want to mention is one really nice paper at KDD a few years ago, which is based on topics and temporal processes. So if you look at this figure here, an interesting aspect about this figure is that there are two users here, UA and UB, and the user A is trying to query Bank of America, Wells Fargo within a small time frame, and then the user A goes away, comes back, and then types in Expedia. The user B, on the other hand, comes in and types in two queries, and without a lot of time gap, queries Facebook. So if you see here, then there are two aspects of this problem which make task extraction easier. One is that oftentimes the queries user type in are topically coherent. So Wells Fargo and Bank of America are both banking and financial institution style queries. So then they would share the same topic. Whereas American Airlines and Expedia are related to the travel industry, so they will be like topically coherent. So if we know that the queries are topically coherent, then maybe they belong to the same task. On the other hand, there is also this notion of temporal closeness. So what's the time gap between some of these queries? So we know that the user querying in related queries in the immediate time frame might mean that they both belong to the same task. So again, the point here being that we want to leverage the topical coherence of queries and the temporal closeness of queries to extract these tasks. How do we do that? So we know that we briefly discussed LDA topic models when we were trying to understand like what type of queries, what type of topics we can extract. So we know that like we can use any off-the-shelf topic model like an LDA to extract some of these topics to capture the topical coherence. But to capture the temporal coherence, we rely on something called Hawkes processes. So Hawkes processes are essentially some of these mathematical models which give us nice intuitions behind how do we model temporal correlations between events. So we're going to spend some time discussing at Hawkes process and then go back and see how we can use Hawk's process along with topic models to extract some of these tasks. So if you're looking at Hawk's process, so Hawk's processes are essentially self-excitation processes. So oftentimes in real world, there are events which occur successively. So if we have an earthquake, then the probability of getting an aftershock, so another earthquake coming in right away, is higher in the near future. But then as and when time goes on, then the probability of getting an aftershock kind of decreases. So there is this like temporal aspect in the occurrence of such events. So similar in stock market. So if you know that the price is going up, then it's likely that the price might go up, and then the variations in a small time frame are really correlated. So this is the property which Hawk's process tries to model, that if there is an event happening, then the chance of that event happening in the near future is going to be high. But then that probability keeps on decreasing as time goes on. So point process allow us to capture some of these characteristics. And essentially, they have this background intensity. So, I mean, if you look at any point process model, then they give you the probability of an event happening at a given point of time. So what is the probability of event happening at any point t? So a point process would say that that this probability of an event happening is divided into two parts. One is a background intensity, and the other one is correlation with past events. So background intensity would give us a probability of any event occurring in a given point of time. So maybe like some event occurs every 15 minutes or every half an hour or every 5 weeks. So that's the background intensity. So in this equation, lambda 0t is the background intensity. So that defines like what's the regular pattern in the occurrence of this event. But in addition, since we saw that there is this self-excitation property associated with these point processes, which means that if an event has occurred in the recent time, then there is a high chance of another event occurring. So that means we want to capture this correlation with past events. So essentially in the formula over here, the intensity is dependent on a background intensity function and also a function which depends on events in the near future. So if you see the summation is ti less than t, which means that we're looking at all the events which had happened so far until now. And then we're going to use the time gap between now and that event in order to decide what's the probability of this event happening right now. So essentially, what this allows us to do is that there is this mathematical function which we could use to define whether or not an event will occur based on have events occurred in the recent time frame. So how do we combine them? So the approach in this paper by Lee et al. Was that we can combine the LDA topic models with the temporal self-excitation Hawk's processes. So if you look at the plot we were looking at here, then we want to capture the topical coherence, and we know that we can use LDA for that. And we wanted to capture the temporal coherence. So the temporal coherence here would mean that if a user has issued a query about a task right now, then there is a high chance the user is gonna issue another query on the same task in the near future. But then as and when time goes on, then the probability of the user issuing another query for the same task decreases. So this is exactly what we want to capture. And this is exactly what's provided by the Hawk's process model. So essentially, we know that we can define a Hawk's process by defining a base intensity function and a function which defines the correlation with past events. So this is where we can say that, hey, look, I'm going to have a base intensity function for my Hawk's process, but also I'm going to influence the next query based on some recent past queries. So the idea over here is that if there is an influence, if the topic between the previous query and the current query is the same, then there's a high chance that they belong to the same task. And essentially, this is where we combine the topic models using Hawk's process. So we use the topical coherence when defining the correlation between past events. So here we know that we needed a base intensity function and we needed a function to quantify the correlation with past events. So essentially what we do is we train an LTA topic model and then use that to define the correlation with past events. So essentially, if this current query shares the same topic as the previous query or the query in the temporal neighborhood, then there's a high chance that these two queries belong to the same topic. So this would give us a way to kind of exert this influence between queries if and only if the two queries share the same topic. And if the queries don't share the same topic, then they're not going to influence each other. So that's another way of understanding and extracting some of these tasks from a query log. So far, we have looked at a few of these approaches. And essentially what we're doing is we know that there is a sequence of queries, which is a query log. And we have divided the query log into sessions. And then we can do some clustering on the sessions, or we can do some of these Hawk's process style models on these queries, and then get some of these like tasks, some of these query clusters which correspond to such tasks. So again, like we mentioned before, that task extraction is good, but oftentimes like complex tasks are there, and we don't know whether some of these approaches which we have looked so far will give us some of these complex tasks, because what we have done so far is like essentially different styles of clustering. And when we have looked at clustering, then clustering is just gonna divide a query log into flat clusters. There's not gonna be any hierarchy involved over here. But we know that complex tasks often decompose into subtasks. But the problem is the number of subtasks is really unknown. We don't know beforehand how many subtasks will there be. So this is where we move on to the next phase and start talking about some of these like subtask extraction techniques. And we're going to talk about subtask extraction for about 10 minutes, and then switch on to more hierarchical Bayesian models of extracting hierarchies of tasks and subtasks. Again, I just want to iterate here that if you have any questions, then feel free to post them on the Slido link, and then we can continue some of this discussion there. Cool. So so far we have looked at task extraction, and we are venturing into subtask extraction. And the primary goal of subtask extraction is to decompose complex tasks. So we are saying that complex tasks often decompose into more focused subtasks, like wedding planning. So if you're planning a wedding, then you would do a number of subtasks like finalizing the hairstyles, looking at dresses, printing out invitation cards, finding and searching for vows and rituals, and so on and so forth. So essentially, the number of subtasks which a complex task could have is not known, because it's not that like, yeah, a complex task will always have 4 subtasks. If the task is about like maybe booking a trip, then it might take like 5 or 7 subtasks to do that. So again, really the number of subtasks is not known. And we do know that complex tasks divide into subtasks. So this is where what we want to do is like, we want to rely on some recent advances in Bayesian nonparametrics. So essentially Bayesian nonparametrics allow us to do clustering without specifying the number of clusters which we want. So I'm going to spend a few minutes talking about some background about some Bayesian non-parametric methods, and then we're going to see how we can use some of these in defining the task-subtask structure. So back in 2002, there was this very nice paper on Chinese restaurant process, which is one of the very prominent Bayesian non-parametric approaches. So the key problem this line of work tries to solve is that when we are doing clustering, we do not know how many clusters we should create. So if you're doing k-means, you'll have to specify that, hey, k is equal to 10 or k is equal to 50. So most of these prominent clustering techniques rely on the user specifying how many clusters they want. But then when we are looking at some of these tasks and complex tasks, then we do not know how many subtasks they would decompose into. So then if we do not know, then we cannot provide what k should be. So this is where a lot of recent work in Chinese restaurant processes allow us to do this non-parametric clustering. So we're not going to specify how many clusters there should be, and we will let the model learn from the data. That essentially, our model will decide how many clusters should be there for this specific data. So essentially, what CRPs does is they try to insert elements into partitions one at a time. So imagine that there is a Chinese restaurant and there are tables in this restaurant. So customers will come in and sit on any one of these tables. So a Chinese restaurant process is a generative process which says that the first customer comes in and there's no table yet, so he's going to sit on the first table. The second customer comes in, and this is where things get interesting. Now, when the second customer is here, then he has a he has a choice that either the second customer could sit with the first customer on that table, or that second customer could create a new table and sit on a new table. So let's say the customer two decided not to sit with customer one and then sit on another table. So then we have two tables. On table one, customer one is sitting. On table two, customer two is sitting. Now let's say the third customer comes in. Now again, the third customer has a choice that either he can sit on the first table, or he can sit on the second table, or he can create a new table. Now this could go on and on as new customer comes in. So essentially, oftentimes, whenever a new customer comes in, then they can either sit on one of the existing tables, or they can create a new table. Now, this is what's the underlying philosophy behind the CRP-based non-parametric method is. So imagine these tables are clusters, and these customers are your data points or queries. So essentially, what you're doing is you're not specifying how many clusters or how many tables there should be, but the model is deciding how many tables get created. So how does it happen? So again, like as we have mentioned, that we know that the CRPs work in a customer-centric fashion, that one customer enters a restaurant, the first customer sits on the first table, and then for the subsequent customer, they can join an existing table with some probability, or they can create a new table. So essentially, this alpha parameter controls what's the probability of creating a new table. So let's say I create, like I put alpha to infinity, like a larger value of alpha. So that means if alpha is close to 1, then what would happen is that there's a high chance of each of these customers creating new tables. So then we are going to end up with this extreme scenario wherein each customer creates a new table. So that means there are n number of tables. That means there are n number of clusters. So then we end up with this extreme world wherein n items, n clusters. Whereas if we create alpha is equal to 0, then there's nobody who can create a new cluster. So everybody's just going to sit on table 1. So it's just going to be one cluster. And if we vary alpha between 0 and 1, we're going to get different number of clusters uh, based on some of these probabilities numbers. So again, this is where we are not specifying what the number of clusters could be. The customer, based on some of these alpha parameter values, decides whether or not that customer could sit on an existing table, or the customer really has to sit on a new table. Now, when we look at some of these probabilities, the decision essentially is not currently dependent on which customers are already sitting on a table. So this is where ICML paper in 2010 from David Bree's group created this distance dependent version of CRPs. So essentially what's happening here is that the probability of a user, of a customer sitting with another customer, is dependent on how close that customer is with that other customer. So if you're really close, if your distance is less and your similarity is high, you're going to go and sit with that customer on that table. Versus if your distance is not that much, then you're going to create a new table. So again, now we get this flexibility of using distances between items I and j in order to do this like non-parametric clustering. So now we could apply this to the search query domain. And so we had a paper at NACL in 2016 wherein we were trying to use and model search task and subtask extraction problem using the distance-dependent version of the Chinese restaurant process. So essentially what we say is we say that customers are the queries and tables are the subtasks. So we don't know how many subtasks exist. We don't know how many tables are going to get formed, but then we are essentially relying on defining the right distance between queries in order to give us the correct number of subtasks. So essentially, there is a generative process here. So for each query, we draw an assignment from the DDCRP prior, and this will give us the table in which the query sits in. And for this table, we can learn some of these parameters. So essentially, we can follow the same process as we described before, as long as we are able to define the distance between any two queries ij, we can follow the DDCRP model and then run it over a bunch of queries, and that will give us the subtask belonging to that complex task queries. Now, this is heavily dependent on how we define the distance function. So again, like one of the basic techniques here would be that we have a gift sampler which draws from this distribution. And the first part of this probability here is the DDCRP prior, which we have defined before. And the second part is the likelihood model. So the likelihood model can say is like that how likely are these bunch of queries to be together. Now, we know that quantifying the distance function is important. So this is where we can leverage some of these like word embeddings. So what we can say is like, hey, just train a word-to-vec or embedding model, learn representations of these queries, and then a cosine similarity between some of these queries would give me a distance function. So essentially, what we can do is we can run this model, have the gift sampler iteratively draw from the following distributions, which is derived from some of the equations we showed before. And once we run this, then we would get the query links will give us the subtask clusters. So essentially what we're doing is that we're looking at a complex task, which is like, let's say, planning a wedding. We're looking at all the queries in this complex task. We do not know how many subtasks exist in this complex task. So then we're going to run a DDCRP model on top of this and divide it into n number of subtasks without specifying how many subtasks we know beforehand. Cool. So just a recap, right? Where are we? So we're talking about how do we learn from users. And in learning from users, specifically in the web search domain, we want to understand what the user need and task is. And we've looked at some query intent understanding techniques. We have started to look at some sessions. Then we went from sessions to task. And we've looked at a few approaches of task extraction. Then we have shown that, hey, complex tasks exist and they should be divided into subtasks. But now we ask the question that, is it recursively true? Can we even further divide some of these subtasks into further subtasks? And is there a hierarchy of tasks and subtasks, which we really should be thinking about? So this leads us to the next line of work, which we did when I was doing my PhD at UCL. How do we extract these hierarchies of tasks and subtasks? So essentially, if you're looking at a task like planning a trip, then planning a trip is a complex task, which is essentially divided into many subtasks, like finding information about visas or flight booking or accommodation booking or finding places of interest. And if you're looking at any one of these, right? I mean, if you're looking at accommodation booking subtasks, then even that subtask gets divided into finding cheap hotels, finding information about Airbnb, looking at couch surfing options, maybe looking at accommodation which is closer to some places of interest in the city and so on. So essentially, such tasks tend to be hierarchical in nature. So we can go on and divide a subtask into further subtasks and so on. So most of the previous work we have looked at, they present tasks as flat structures. But now we want to consider hierarchies. One possibility is just to consider hierarchical clustering. So maybe what we can do is just, instead of doing a normal clustering, we could look at some hierarchical clustering and then run it over and get these task hierarchies. But that's not really that useful, because there is no guide on the correct number of clusters. And most of these hierarchy clustering gives us binary trees. I mean, we've seen before that this is not a binary tree. There is like the first root has 4 subchildren, the second one has 2, the one here has 3. So binary trees are very restrictive, and most of these hierarchical clustering algorithms work on these binary tree assumptions. So this is where we need models that can represent trees with arbitrary branches. Like we don't need to specify that only a root can only have 2 children. We can have like arbitrary branching structure. And that means that the model is rich enough to capture all the different intricacies in this complex task subtask hierarchical structure. So this is where we rely on some recent advances in Bayesian nonparametrics again. And essentially, we look at Bayesian row trees. So what Bayesian row trees do is they represent a set of nodes as, so they represent the tree as a set of partitions on the data. So essentially what we can do is we can look at a bunch of queries A, B, C, D, E, F, and then try to partition it recursively. So let's say we start with all these 6 items in the same node, and then we partition A, B, C into one, and then D, E, and F into separate. Then we go again and further subdivide A, B, C into 3 different trees. So this would give us this very nice, rich structure of this tree. So the first node has 4 children, and this node over here has 3 children. Now, we are able to do this because right now we are partitioning it in a way which allows for multiple branchings together. So how do we construct this from the data? So what we do is we build upon Bayesian row trees and say that in my tree, each node will correspond to a task. So for each node, I'll have a bunch of queries, and that will correspond to a task. And then the goal would be to subdivide them into subtasks. And each task will be represented by a bunch of queries. So what we want to do is, the goal is to find a tree structure that maximizes the probability of the likelihood of like observing the set of queries we have. So essentially what we're saying is that there's a mixture over partitions of these data points, and this is the function which we want to maximize. And the tree which maximizes this function is going to be the tree which we learn. So there, I mean, if you're looking at a tree, there could be like an exponential number of trees for any number of nodes and children. And the different structures of these trees will capture the different task subtask structures. And what we want to do is we want to find out what is the tree structure which tells us that this is the task subtask structure present in my query log. So what we want to do here is like we want to approximate this using dynamic programming. So we want to say that, hey, look, this is computationally intractable. So maybe I can split it up and say that the probability of observing a bunch of queries given a particular tree is dependent on a function f of the likelihood of observing those queries in the same task, and a function of the subchildren of that tree. So let's say that, okay, so let's just take a step back and say that I'm going to start with each query as a potential tree. And then I'm going to end up with like, at the start, we'll have a forest of trees because each query is a potential tree, and then we're going to start joining them together. So initially, we start with a forest, which contains a single tree for each query, and then we start merging these together. So let's say we have 2 trees which we want to merge. Now, what we can do is we can try to do 3 types of merging operations. So if we have trees T1 and T2, then let me actually just make sure that the figures over here are, yeah, never mind. So let's say we have 2 trees, T1 and T2. Then there are 3 different types of merge operations which will give us the rich complexity of the structure of the tree we want. So remember, we said a while ago that we don't want binary trees. We want like really complex, arbitrary branching trees. This is what's going to give us those. So if we have two trees, T1 and T2, and if we do the join operation, then we end up with a binary tree, which will have both of these as subchildren. Instead, if we do a collapse operation, then all of the children of the two trees get together combined at the same level. So then we end up from having two separate trees to a single tree, which has all these five subtrees as just its children. Or we could do an absorb operation. So absorbing means that we absorb one of the trees into the other tree as one of the additional children. So here we are saying that Tj gets absorbed into the Ti. So Ti already had trees A, B, and C as children, and now Tj is another child of the tree Ti. So if you think about this, then these three operations guarantee that we can create any arbitrary tree structure with this. And it does not restrict us to just the binary trees, which was the case in hierarchical clustering. Now, the question is which trees to merge and how to merge them, right? I mean, what we can do is like, we started off with a forest, which was like every query is a separate tree. And then we start like randomly picking up two trees and see like, okay, should we combine them or not? So how do we combine them? So now we have three approaches, three different ways of combining them. Now we're going to try all three and then pick up the one which gives us the maximum base factor improvement. So we're going to look at the merge tree and then compute the score. And for the merge tree, which has the highest value of this score, we are going to pick up that particular combination. So essentially, like for each pair of trees, we do this merging and then just pick one of these merging criteria, which gives us the maximum score. And then we do that for across all pairs and then pick up the one which has the highest. So that gives us a huge tree, which has a lot of like fine-grained leaves, which are just like singleton queries, right? Because what we did was we're doing bottom up. So we're starting with like each leaf as a tree, each query as a tree, and then we're starting merging these together. Now, once we have the entire tree, then what we really want to do is like we want to prune this tree from below, and then just remove the leaves as such. So we do a tree pruning operation, which is based on a task coherence. So we define a measure of task coherence at whether or not these queries together make sense. If they make sense, then we just kind of prune subtrees below that. And if they don't, if the task coherence is low, then that means we can further subdivide it. So we keep the children and don't prune the tree from there. So again, this approach allows us to start with a bunch of queries and then iteratively start constructing these trees. And then after pruning, we'll get this tree, which will have a structure of task. And each of these tasks will be subdivided into different subtasks. Now, this is an example for a bunch of queries which are around Red Bull. And then we know that, like, I mean, if we start with these queries, if we run this model, then we end up with three children in the fruit. One of is around ingredients, the other one is around side effects, and the third one is around like US policy and banning on the government policy around Red Bull. And if you're looking at like the Red Bull side effects, then again, like there are health effects and there are different clusters of side effects. So again, as we see here, there's no restriction of this to be a binary tree, and there's like a rich structure in this tree as well. So the take-home message here is that hierarchies as such provide a more naturalistic view of complex tasks. And we're looking at like Bayesian non-parametric approaches for task and task hierarchy extraction. And we get a lot more richer and expressive models of task, which give us like valid, useful hierarchies that relate to subtasks. So let's take a look at what we've done so far. So far, we have motivated the need for understanding tasks in the web search domain. And in search, it's a different paradigm because the user explicitly provide the search query. So now that we have millions of users using search engines on a daily basis, we have access to like billions of query terms. And from these query terms, we can apply any of these approaches at scale, come up with clustering, come up with hierarchies of these tasks and subtasks. And that will give us the space of the task the user is attempting to answer from the search session, right? And this is where once we have these tasks, then we could do a lot of these like personalizations, right? So imagine we have all these search log data, and then we extracted these task hierarchies, and now a new user comes in. All we have to do is like find out whether this query belongs to which specific task in this hierarchy, and then we can do all sorts of like task-based personalization and re-ranking there. But this is explicitly the case for web search because users are providing their query over there. What happens when you go to the Netflix homepage? So in a recommendation portal, users don't necessarily provide their search queries because if you go to the homepage on Spotify, you get shown recommendations. If you go to Netflix homepage, you get shown recommendations. If you go to Pinterest, then we don't wait for users to query something and we fill the homepage with like the recommendations as such. So essentially, this is where there is no explicit query. And then also we want to understand what the user goal is. So we're going to depart from web search and present a couple of case studies. The first one is Pinterest, some recent work from Pinterest. And the second one is some recent work from Spotify in understanding the user intent and user task in some of these recommendation systems. So the work I'm describing now is based on this paper at www a couple of years ago. And this is coming in from Stanford people and people at Pinterest. So the idea of this paper is like, can we predict intent using the activity log? And the idea over here is that because the user is not really specifying a query, then we want to be able to predict intent using user interaction information. So the motivation behind predicting intent is that intent precedes and predict any future behavior. And once the user knows what their intent is, then it kind of directs how the people use the different systems. So again, like we cannot infer intent in like as we did in search because there is no explicit query. We can only observe user behavior. And another challenge is like intents can vary significantly, right? So again, like if you think about, if you go to Pinterest, so Pinterest is essentially a website wherein you can find creative ideas and like find different items and images and pin them onto your board. If you haven't had a look, then go have a look. It's a pretty large scale website used by over 100 million users, I guess. So again, like if you're looking at identifying intents, then people use Pinterest for a number of different things. So the question becomes like, how do we start to organize them into different intents? So one is like the first attempt could be goal oriented versus experiential. So some of these are goal oriented, like I am explicitly searching for car images, or I want to create cupcakes. So I'm looking for cupcake recipes, or I'm looking for gardening ideas. So these are mostly goal oriented versus the other one are just about experiential, right? I'm bored, I'm just looking around. The question then is like, is there a better way to quantify and predict intent? And this work here, the paper we are talking about here is like an approach for intent prediction models. So this essentially relies on behavioral analysis and large-scale survey. So the behavioral analysis is how users behave on the platform. And it kind of identifies that there are two key dimensions of intent. One is the goal specificity, and the other one is a temporal range. So goal specificity is how well-defined is the goal. So users often have the goal and intent, but oftentimes it's like very, very specific that this is exactly what I'm looking for. And oftentimes it's like pretty broad that anything around this area would be okay with me. So gardening is really in between. Killing time, just kind of leisuring around on the internet is less specific, and cake recipes is like a lot more specific. If you're looking at temporal range, then when will the goal be fulfilled? So there are like short-term and long-term goals, which is the temporal vicinity in which a goal could be achieved. So then instead of just looking at some of these categorizations based on experience or goals, we can look at like these spectrums, like are they specific and what's the temporal aspect of these tasks? So essentially here, what they started doing was the Pinterest people conducted a user survey in asking whether users had a goal when they were visiting, and the goal of specificity they found out was really like bimodal. That it's not the case that it's uniform. Often people have non-specific goals, and often people have specific goals. So I'm going to skip some of these. Essentially, like again, the question then becomes like, can we predict intent when the user comes onto the app? So if we can quantify some of these characteristics of the users, right? Which is what are their demographics, what are their historic activity, what is the current activity, and then we can use that to predict what their intent would be. So the question then becomes, how quickly can we predict intent? So at 10-minute period, we can get AUC scores of about zero point 0.8. But then we don't need later. So essentially what we see here is that once you have observed what the user is doing for the first 10 minutes, then you have enough information to predict what the intent in the current session would look like. So you don't need to keep on observing until like 30 minutes, because up until 10 minutes, it's going to be okay. And you have enough information to predict what the user is trying to do. And here, the question could be like, the intent can be predicted even more quickly, because you really don't want to wait for 10 minutes, right? Because if the user has been on the platform for 10 minutes and you're not serving good recommendations, then they may or may not stay on the platform and just get annoyed and go away. So you want to do intent prediction as quickly as possible. So the findings from this work says that if we use some of those features, then we can do some sensible intent prediction within like a minute of users' activity on the platform. So again, like oftentimes historical features are there, so intent can even be predicted before a session begins, because we know what the user was up to until like yesterday, or what have they been historically doing on the platform, and that could guide what kind of intents they would have in the next sessions they have. So again, like understanding intent is going to be pretty useful, because once we know what the intent is, then we could design separate interfaces for browsing versus doing. So if they have a task in mind, then maybe Pinterest can have a dedicated UI and interface to promote these task-based activities on the platform. And then again, like we can provide like more situational recommendations or suggestions based on these changing intents users might have. So again, like intent understanding is like super useful, because the more you know, the more you can adapt. So if you know more about content, then companies like Zomato and Yelp would benefit from it. And in general, like if you know what content the user wants to experience, then Instagram style platforms would benefit from understanding intents. So here we took a brief overview of how do we look at intents on the Pinterest platform. I'm going to present some work which we recently did at Spotify in understanding intent. So this is work at Spotify, and this is essentially coming in from the www paper at the web conference we had in last year. And the goal of this work was to understand intents and then use the intent information to better predict user satisfaction. So if you go to Spotify, right? I mean, if you're not querying anything, if you're on the Spotify homepage, then how do we know what the user's intent is? So the user goes on their mobile, they open up the Spotify homepage, and then we show them some playlist without knowing what the user intent could be, because the user never explicitly writes a query in there. So this is where we want to understand the space of the intents users could have when they're using the homepage. So what we did was we conducted in-person user interviews. We got in a bunch of people and then asked them a bunch of questions around their music listening habits, their Spotify usage, and asking about what all their good and bad experiences have been. And we try to ask them questions like, what is it that you were trying to do in your current session? So that gives us the space of intents which we could be looking at. So essentially, we also did a survey inside the app wherein we were asking users, were you happy with Spotify, and whether or not was these one of your intents behind using the homepage. So essentially, once we do all that qualitative analysis, then we show that we're able to come up with like 6 different types of intents users might have. They're broadly grouped into passive listening and active listening. So often users use a Spotify homepage to quickly access their playlist or save music, or they just want to maybe play something in the background, or they want to discover new music, or they want to explore new artists, which means that they're like a lot more actively engaging with the platform. So again, we did some work around looking at survey analysis data and looking at qualitative behavioral information to extract some of these intents. Now, once we have these intents, then we can predict user satisfaction. So we did some experiments and showed that understanding intent is really helpful, because if you know the intent, then you're able to better predict user satisfaction than if you do not know the intent. So essentially what you can do is, like, let's say you have like 6 intents. So one way to do a satisfaction model could be like you just throw away the intent and not consider it. So that would be a global model, that I don't care what the intent was. I do not know what the intent was. I'm just going to train a simple single model, which is a global model, to predict whether the user was happy or not. Or we can do a per intent model. Like I'm going to give regard to what the intent was and then train separate models. Or we could do some sort of like multi-level modeling wherein we're reusing a lot of insights from across different intents. So in our experiments, we found that considering intent is crucial. So we saw up to 10% improvement in satisfaction prediction when we consider intents than when we don't consider intent. So again, intent understanding is like super important at any of these like media companies and recommendation portals. And different from search domain, it's really like the user is not specifying a query on the homepage. So we'll have to come up with like other ways of identifying user interest and user intent, which is something which like Pinterest and like this work at Spotify touches upon. Cool. So we are almost at the end of the first part and the first video. So here, like we started by asking this question: what is a task, and what different types of tasks people do across different platforms? How can we extract these tasks and subtasks using hierarchical models? And what does task mean in the recommendation system? So like in search, people have queries, so we can use like some of these task extraction techniques. But in recommendation systems, people may not pose queries, and then we looked at some other ways of understanding these intents in recommendation platforms. So essentially, the take-home messages so far is that it's important to consider user needs and tasks. And in search, there is like different granularity at which we can understand user need. One is at the query level, identifying query intents. One is at the session level, and then finally it's at the task level. And when we look beyond search, then there are user goals and intents which we can extract, uh, which we can extrapolate based on user behavior data. But then there we rely on qualitative and quantitative approaches to do that. So again, just to contextualize where we are at the end of phase 1. We looked at understanding user tasks and needs. And in the next phase, in the next video, we're going to talk about how do we learn user representations. We're going to focus on a lot more recent published work around recommendation systems and some recent industrial papers, which say how we can learn representations of users. And then in the third part, we're going to talk about how can we leverage these user interaction information to come up with better evaluation and metrics and experimentations. So just a trailer would be that we're going to talk about some really recent state-of-the-art methods of representation learning, and also some methods about like getting explicit and implicit feedback from the users. So if you have questions so far, then just remind you that you can go and post questions on the Slido. The link is there, the event code is there. Just post the questions, and then I'll be happy to answer them. So in the next talk, in the next video, we're going to talk about starting with phase 2. So see you there.